So the next type of transformation involves a certain type of reflections across either the x-axis or the y-axis. As an illustration, you can see here's our parent function in black of just y equals a positive x squared. Oh, they wrote that right there. I didn't recognize that. And then if you were going to graph the g of x equals the opposite of x squared, y'all, this is understood to be a -1 times x squared. That really makes all these y values that were positive negative and vice versa. So that's what it means now that our key points are 0 and the opposite of 0 still just 0. But 1, 1 would now be 1, the opposite of 1, -1. 2, 4, now it is at 2, -4. And -1, 1 is now at -1, -1. Okay, and so the -2, 4 key point is now at -2, -4. So you're going to know if you have a reflection about the x-axis if you have a negative out front of your function like that. Okay? Now, a good one to illustrate this next thing with is with this root function y equals square root of x. Okay? Here it is again, key point 0, 0, 1, 1, 4, 2, 9, 3, 16, 4. Okay, so forth. Okay? Now, if you're going to graph g of x equals the square root of a negative x, and y'all, that is our function evaluated at a negative x. That's what they're calling g of x. Then what that was going to clue you in on is if you've got the negative inside there, then that's going to clue you in that you're going to reflect everything across the y-axis. Okay? Because now that you're doing the opposite of these radicand values, the only things that are going to be defined are going to be if these radicands stand for negatives. Because the opposite of the negatives will ensure that our radical underneath our square root, the radicand is positive. Okay? So that is why we have a reflection about the y-axis if that should occur. Okay? Summing up this information, if we've got a parent function y equals f of x, then the graph of y equals the opposite of f of x with the negative out front is a reflection across the x-axis, whereas y equals the function evaluated at negative x is going to be reflected across the y-axis. Okay? So on example 6, which again, y'all, is different from the one in the ebook. All right, so if you want some more explanation on some of this, you might want to go look at example 6 in the ebook. But for our example 6, it says the graph of y equals f of x is given. It's this little semicircle looking thing. Okay. On part A, they want us to graph y equals the opposite of f of x. And so that is, since it's out front, since the negative is out front, that means we're going to reflect everything about the x-axis. Okay? So this key point right here at 2, 2 is now going to be at 2, -2. Okay? 0, 0 reflected about the x-axis just sits still and stays right there. And 4, 0 stays right there as well. But this one that's like at 1, about 1.7 maybe, will now be at 1, -1.7-ish. And instead of 3, 1.7 or 1.8, whatever that is, it's now at 3, -1.7 or 1.8-ish. So what I'm sketching here in the orange is my graph of y equals the opposite of the blue function. That's with the reflection about the x-axis. Okay? Now, on part B, we're going to graph y equals the function evaluated at a negative x. That tells us that we're going to take this blue semicircle and reflect it about the y-axis. So now we still have a key point at 0, 0, but instead of being at positive 2, when we reflect that about the y-axis, we are at now negative 2, positive 2. And instead of us being at 4, 0, we are now at negative 4, 0. And we can also reflect some of those other points in here that we had to just kind of eyeball. But this little green semicircle here that I am drawing in as best I can is the reflection of our parent function, the blue function, y equals f of x, about the y-axis. And we knew we were going to have that because it was the function evaluated at a negative x. Okay, let me write that. I'm trying to write this. Y equals the function evaluated at a negative x. There we go. That looks better, and I might be able to sleep tonight because that's better. Okay. Okay.